Welcome back, everybody. In this video, we're working on section 4.6, which is about exponential and logarithmic equations. And so basically, we're going to start by looking at some exponential equations, then some logarithm equations. The first kind of main property that we'll use to help us solve exponential equations goes like this. As you know, both the exponential and logarithmic equations are one-to-one, and so we get a one-to-one property. So it says for any algebraic expressions, S and T, and any positive real number B that isn't equal to 1, B raised to the S power equals B raised to the T power if and only if S equals T. So a little more on background or detail on that, and then we'll actually use it. So as you know, with any function in the whole world, if A is equal to B, then f of A equals f of B. And that's just based on how functions work, right? If you have two eggs and you crack them both, you've got two cracked eggs. All right, so if you have two things that are equal and you do the same thing to them both, then you get an equal result. And this is just common sense, almost. All right, so then if additionally f is 1-to-1, okay, then if f of A equals f of B, then A equals B. So what that means is if you know that the function is 1-to-1, and if you know the outputs are the same, then that means that the inputs will have to be the same. Notice that that's not true if f is not a 1-to-1 function. For example, we know that 7 squared equals -7 squared. That is, they're both 49. But of course, that doesn't imply that 7 and -7 are the same. But if you have two functions that are 1-to-1, knowing that the outputs match will ensure that the inputs match. And that's basically what this 1-to-1 property is saying, but they've said it specifically for exponential functions. It is, however, true for any 1-to-1 function. And that's the basis for how we're going to solve this first equation. So this one says we have 10 raised to the 2x minus 3 power, and that's equal to 1/10. And so what we're going to do is try to first rewrite both sides as powers of the same thing, and then we'll use that 1-to-1 property. So the left side is already written as a power of 10. Okay, and so remember that the right side, 1/10, is the same as 10 raised to the -1 power. And so now the thing is we're going to use the fact that this exponential function is 1-to-1, and we can conclude that 2x minus 3 equals -1. Note that we are not dividing both sides by 10 here, right? Because this is an exponential function. This is not multiplied by 2x minus 3. This right side isn't 10 multiplied by -1. We're just using the one-to-oneness of the exponential function here to conclude that if the outputs are the same, their inputs have to be the same. Okay, so now just simple algebra here. We'll add 3 to both sides. So that will give us 1 for our solution. Okay, and how we got that was by rewriting both sides as powers of the same thing, and then concluding that if the outputs match, then the inputs have to match as well. All right, so we have another one for us to try. This one is from our textbook, so we'll try that now. So it says solve 5 raised to the 2x power equals 25 raised to the 3x plus 2 power. And so what we're going to want to do is try to rewrite both sides as powers of the same thing. And I think all of us here are going to pick out 5 for that. The left side, that's already 5 raised to the 2x power. The right side, 25 is 5 squared. So I'll rewrite 25 as 5 squared, and that's still raised to the 3x plus 2 power. Now we're going to use a exponent rule on the right side to write that. When you raise a power to a power, you multiply exponents, right? So that will be 6x plus 4 for the exponent. Okay, now that we have the outputs matching, 5 raised to the 2x power equals 5 raised to the 6x plus 4 power, Since the exponential function is 1-to-1, we can conclude that 2x is equal to 6x plus 4. Okay, solving that little equation for x, we'll have negative 4x equals 4, so that x is negative 1. It just so happens that the solution there is negative 1. The answers aren't always going to be 1, negative 1. Our first two examples just happen to be it. Also, one more thing, as you remember, the input to the logarithm functions has to be positive. Remember that the domain for exponential functions is all real numbers. So there's no issue or problem with the fact that that x came out negative. Okay, so this has been our first couple of examples of exponential functions. When we don't have the ability to easily write one side as a power, both sides as powers of the same thing, then we're going to take a different approach. So here, it's kind of hard to write 5 as a power of 3, right? 5 to the first power is, or 3 to the first power is 3, 3 squared is 9, 3 raised to what power is 5? That's kind of hard to do. So instead, what we're going to do is take the logarithm of both sides. So let's do that. You can take, remember that if a is equal to b, then for any function, f of a equals f of b. So we could just take the logarithm of both sides, which on the face of it looks like it's going to make it more complicated, but it's going to help in the long run. You can use either logarithm, well, any logarithm really, but usually people use either the base 10 logarithm or the base e logarithm, because those are the ones that are in the calculator, right? So most people, most students for some reason have a preference for the common logarithm, so we'll go with it. So log 3 raised to the 2x minus 1 power equals log 5. So we've just used the fact that if two things are equal, then their logarithms will be equal. Okay, and like I said, that makes it look a little worse. But the reason why we're going to do this is so that we can use one of those log properties we learned. So we learned that x raised to the r power, if you're taking the logarithm of an exponential expression, that exponent can come around front as a multiplier. So log x to the r power is the same as r log x. And that's really why we're taking the logarithm of both sides. So that this 2x minus 1, we can get access to that. We'll bring that around front. We'll have 2x minus 1 log 3, and that will equal log 5. Okay, so whenever you're, in general, I guess, whenever you want to try to get access to a variable that's in an exponent, you want to think about taking logarithms of both sides. Okay, so we want to get our x now, so let's divide both sides by log 3. So we'll say 2x minus 1 is equal to log 5 over log 3. And then add 1 and divide by 2. Of course, as always, you need to pay attention to whether you're supposed to give an exact answer or an approximate answer. For this one, it probably would be a nice idea to simplify it some, but as an exact answer, that will do. And again, the overall is we took the logarithm of both sides. Again, I chose the common logarithm for this, just because most people do. But if you use the natural log, that's okay. Just make sure you don't use the log log on one side and ln on the other, okay? Because then it's messed up. All right, so that was the exact answer. Let's go ahead and approximate this thing using a calculator. So let me take and do 1 plus log 5 divided by log 3, and then we'll divide that by 2. I get about 1.2324. Okay, and then if you wish, you can substitute that back into the original equation and check and see if you like what you got. All right, so that has been a couple of exponential equations. We'll come back and do more here in a little bit. I wanted to do first some logarithm equations. So let's see that. So just as with the exponential equations, or exponential functions, the logarithm functions are one-to-one. And so if you know that log of one thing equals log of another, then that implies that the two things you took the log of have to be equal to each other. So that's how we can solve lots of log equations. So here we have the base 5 log of x equals the base 5 log of x plus 1, and that's equal to log 5 of 20. So here I can't exactly use this property just yet because that just says log this equals log that, and this has got two logs on the left side. So what we're going to do is use another of the properties that we learned, the sum rule, to turn this into a log of a product. So that will be log base 5 of x plus 1 equals log 520. Okay, now you have log this equals log that, so you can use the one-to-oneness of the logarithm to say x plus 1 equals 20. And that's a nice little quadratic equation, and you have a lot of experience solving those. So let's go ahead and do that. Luckily for us, I made this one so that it would factor. And so it looks like our two candidate solutions are -5 and +4. Thing you have to be careful of, okay? For the quadratic equation, -5 and 4 are solutions. However, remember that what we're finding is the solutions to a log equation, so they have to fit the domain of the logarithm. -5, I wouldn't be able to plug it into that first logarithm, right? Because the logarithm has domain 0 to infinity. So the -5 doesn't work. We will only have this one, only the 4. The -5 is what's called extraneous, or extra, some people say. And that means that it is kind of a solution to the quadratic equation, but it wasn't a solution to the original equation. Okay, so here we had to apply a log property, and then we were able to basically say, okay, logarithm of this equals the logarithm of that. Basically, out of the two different kinds of logarithm equations you're going to see, they will come in more or less two kinds. Like the ones like we just did, where you have logarithm of one thing equals logarithm of another, in which case you're going to use the one-to-one property of the logarithm. As you know, if you have a situation where you have a logarithm of something equals a number, I just made that up, the base 5 logarithm of x equals 12, if you don't have it log equal to log, if you have it log equal to number, then what you want to do is rewrite it in exponential form. So this will be 5 raised to the 12th power is equal to our x, okay? And that's a nice big number. Okay, so that's good. Okay, so we're going to do a couple of more examples next. So keep in mind the overall guidance that we want to, if it's log equal to log, use the one-to-one property. And if it's logarithm equal to a number, we want to rewrite it in exponential form. All right, so let's try these next two examples next. So on the left, we have the natural logarithm of x plus 2 is equal to 6. So this has a logarithm just equal to a number. So I'm just going to rewrite that in exponential form. Remember that the natural logarithm, if it helps you, you can rewrite that as log base e, just like that, if it helps you get the right things in the right places. So then putting that in exponential form, we'll have e raised to the 6th power is equal to x plus 2. So then x will be -2 plus e to the 6th power. Okay, and that's it. We'll just leave it at that. All right, next we have log x minus 4 is equal to 3. So that's 10, right? There's a common logarithm. 10 to the 3rd power is equal to x minus 4. So 1004 is our x. Okay, in both of those, they were just logarithm equal to a number, and so we just rewrote them in exponential form to solve. Okay, in this next example, this one, we're going to use a log property to combine the two logarithms. So we'll have log x minus 3 is equal to 1. Okay, remember this is a common log, so we can look at that as base 10 log. 10 to the first power is 10, so 10 is equal to x minus 3. Okay, so once again, nice quadratic equation to solve. And those should be pretty comfortable and familiar with you or for you by now. So it looks like 5 and negative 2 are two possible solutions. However, examining the original equation, it's clear that we can't have it be negative 2 because of that logarithm. So we're going to discard the negative 2 and just have the 5. The negative 2 is an extraneous solution. Okay. All right, here's one from our textbook. In this one, it's got an e in it. There's just a single exponential expression in there. We're going to end up taking the logarithm of both sides to get access to the variable in the exponent. You'll notice that this was an exponential equation rather than a log equation. So before I take the log of both sides, I'm going to divide both sides by 3. So we'll have e raised to the 0.5t power equals 11/3. Now we're going to take the logarithm of both sides. And I know most people prefer the common logarithm, but since this problem has an e in it, it makes most sense, or it's natural, to use the natural logarithm. So let's take the natural log of e, 0.5t, and that's natural log 11/3. Okay, so then we'll bring that 0.5t around front using our kind of third log property. Nothing happens on the right side. And then natural log of e is 1. So we have 0.5t is equal to natural log 11/3. Okay, so then we're going to divide by half, we'll multiply by 2, depending on how you want to look at it. So t will be 2 natural log 11/3. Okay, or if you want to simplify that a little bit, this will be natural log 121/9. Okay, I'll leave it to you to figure out how I did that. Let me know if you don't get it or if you have any question. All right, so that takes us to the end of this first part. We're going to continue in the next video by looking at some examples involving solving either exponential or logarithm equations. In the meantime, let me know if you have any questions and have a great day.